My hope is you have this class topic calendar printed out so you know what you're supposed to do each day, and these are what I plan to talk about each day. So for example, today is October 4th, so we're going to talk about section 6.1 sine graphs. We're going to move on Wednesday to section 6.2. So today I expect you to start the section 6.1 homework. And we started section 5.5 last week. We're done with chapter 5, although you may not be done with your homework. That last day to turn that in is today for a grade, unless you use a late pass. So we are now in week 3, starting chapter 6. After we do chapter 6, we'll have a midterm exam, and we're going to do about a section a day. So in about a week and a half, 2 weeks, we'll be done. 2 weeks, we'll be done with chapter 6, and then we'll have our first exam. So chapter 6 is about what's called sinusoidal graphs, and we'll see what that means right now. So we've looked at sine, cosine, tangent, and the other trig functions in 2 different ways. One way as coming from XY coordinates on a circle. And we have some special angles that we need to be familiar with: pi over 6, pi over 4, pi over 3, pi over 2. Here I drew a radius at 2 pi over 3, so I want to take a look at that one for a second. As we come around, 180 degrees is the same as pi radians. Going around 3/4 of the circle takes us to 3 pi over 2 radians, and coming back to the positive x-axis here, that would take us to 2 pi radians. If I could write with my pen. My Zoom screen is in the way. Let's move that over there. Should be good. One more time. 2 pi. There we go. So let's focus on this radius right here at 2 pi over 3. We've known for a little while now that that's called the standard angle measured counterclockwise from the positive x-axis. So that's my angle of 2 pi over 3. Now, from that point, I can think about tracing over to that point by using the x value and the y value. And then when I do that, I get this right triangle here. That right triangle has a reference angle. Reference angle is to the nearest part of the x-axis, and so that would be pi over 3. Right? In this case, that would be pi minus 2 pi over 3. And we can view the sine and the cosine and the tangent as related to this triangle here, or we could view it as being related to the circle. A couple ways to deal with that. Now, down here, I wrote down some values related to just the sine. So on the circle, the sine is the y value. So on the circle, y is the sine of theta when I select a radius of 1, which is what I'm doing here. So this is my unit circle, centered at the origin. And so the y value at 0 radians is 0. The y value at pi over 6 is a half. At pi over 4, it's about 0.7 square root of 2 over 2. At pi over 3, it's about 0.86-ish up here, square root of 3 over 2. And at pi over 2, the sine gets its maximum y value of 1. Right, so at this point right here, sine of pi over 2 is 1. And then as we move that angle further along here in that positive counterclockwise direction, then the sine of 2 pi over 3, right, that radius I was referencing earlier, that would have to be the square root of 3 over 2. So I mentioned previously you should have the x and y values of these special angles in the first quadrant memorized, and then we can use those to generate other ones. What we want to do next here is move away from the triangle and the circle for a moment and just think about the relationship between the angle and the value of the sine. And I mentioned before, very beginning of class, that the y value on the unit circle, which is also called the sine of the angle, is a function of the angle. Right? So Sine depends on the angle. When we have one variable depending on another, they have a relationship, and sometimes that relationship is a function. In this case, the sine is the function of the angle. Now, usually when we talk about functions, we write things like y equals f of x. But we can use different variables besides y and x. In this case, I'm going to stick with y for the sine. And instead of x, I'm going to use theta, because that's the changing variable I'm watching up there. I'm watching the angle change. That's making the y value on the unit circle change. So here I have y as a function of theta. And that function is specifically called the sine. And our calculator has a sine button. So what I want to do is I want to look at what does the graph of y versus the sine of theta look like. So to do that, over here, I've drawn a new set of axes where this horizontal axis is not x, it's theta. That's my independent variable here. My y value is my dependent variable. And it's going to be whatever the value of the sine of that angle is. So now we're going to grab some of the points that I have in my table. Let's pick a color. So for example, my graph, my function has the point 0, 0. It has the point pi over 6, 1/2. Okay, so let's say I have pi over 4 here. Pi over 6 is just a little smaller, about right here. 1/2 is about right there, so I should have a point around right there. Pi over 4, we get 1 over the square root of 2, or square root of 2 over 2. Check it on your calculator. That's about 0.7, 0.71. So if that's a half, 0.7 is probably going to be around right here. So I should get that point. Pi over 3 is a little bigger than pi over 4. It's about right here. And that's going to give me about 0.86, almost 0.9 for the square root of 3 over 2. So a little bit higher. It's going to be around there. And then at pi over 2, that's going to give me the highest point up here of 1. So my function is rising up toward that point right there. But then the y value drops on the unit circle, right? So if I go the other way, keep going along at 2 pi over 3, so that would be about here on the x-axis, I'm going to get that 0.86 value, which is around here. At pi over 4, it's going to be about 0.7, and sorry, 3 pi over 4. And then at 5 pi over 6, which is about right here, I'm going to get 1/2, which is around right there. And then at pi on the circle, right, the y value is 0 again. So I'm going to get the point pi 0. So this function drops down. Now, I can make this angle keep going here. So right now my angle is stopped at pi, but I can keep going down here to 7 pi over 6, over here to 5 pi over 4, over here to 3 pi over 2. So I'm just going to get a few more of those. So let's say we're going to do this one right here. So what angle is that? So that's right in the middle of pi over 4 and 3 pi over 4. So it's related, so sorry, 3 pi over 2. It's related to 45 degrees or pi over 4. So this would be 1 pi over 4, 2 pi over 4, 3 pi over 4, 4 pi over 4. This is 5 pi over 4. And y values related to pi over 4 are related to the square root of 2 over 2 or 1 over the square root of 2. So at 5 pi over 4, my y value is negative. And it's going to be square root of 2 over 2. Whoa, it's a mess of 2, which is around negative 0.7. So let's scale my x-axis out a little farther. If from here to here is pi, I'll make another jump of pi over here. So right over there is about 2 pi. Right in between would be a jump of half pi, or 3 pi over 2. And then right in between that is the one I was just looking at, which should be 5 pi over 4. And I calculated at 5 pi over 4, I should get negative 0.7-ish. So down here is negative 1, negative 0.7. That right there looks a little bit too close to the axis. Let's fix that. There we go. Negative 1 should be right about there. All right, so negative 1/2 would be about here-ish. Negative 0.7 is about there. So coming across. So I should have a point around right there. At 3 pi over 2 here, I get the negative 1 for the y value. So then tracing over here, I'll have a negative 1. And then when I sweep back to 2 pi or 0 here, I'm going to get the y value is 1. So I'm going to get another point right there. And we have that symmetry in between. So if this is 5 pi over 4, this would be 6 pi over 4, 7 pi over 4 would be around here. And I'm going to get that same y value. So 7 pi over 4 is going to be right in between here. And I'm going to get a matching y value there. So this is what happens when I make that graph. Now, when you first look at this, you might say, oh, that's interesting. This looks like a semicircle. Like this is a semicircle up here, but it turns out this is not. So this curve that we get here is very unique. And it is not a semicircle. And I can prove it's not a semicircle if I just look at the values here. So the distance across from here to here is pi, right? If it were semicircle, that would be the diameter, and the radius would be pi over 2. Well, pi is about 3, right, on a bad day. So 3/2, that's 1.5. So horizontally, it looks like the radius is 1.5. Vertically, however, it looks like the radius is 1. And if it's a circle, that can't be. Radius has got to be the same. So you might say, oh, maybe it's an ellipse. Turns out it's not an ellipse either. And we'll look at ellipses later in the quarter. So I'm just going to whip out a graphing calculator. Take a look at this curve. I'm going to use GeoGebra. And let's use the regular calculator today. So I want to graph. And on most calculators, your independent variable has to be x, even if on paper you're calling it something else like theta. So here, to graph that, I would have to graph y equals the sine of x. And so it draws a whole bunch for me. Now, it drew way more than I did. I only drew this part of the curve between 0 and over here would be 2 pi. Pi is about 3.14, so 2 pi is about 6.28. Here I can see I should get a point there, root, which is next intercept, of about 3.14. So you can see that's approximately the point pi 0 right there. This up here would be the point pi over 2, 1. And this is what the sine function looks like. And notice it just keeps over and over again making this wave. And that wave is definitely not a circular arc. It's definitely not an ellipse. If you aren't familiar with ellipses, I'll graph one here just for fun. Let's graph the center one at the origin, x squared. So maybe you saw these in a previous class. Let's go x squared divided by 4 plus y squared divided by, how about 1 equals 1. So an ellipse is like a stretched or squashed circle, depending on your perspective here. And one thing to note, when that ellipse comes down to one of its turning points here, if you zoom in there, let's see, how do I zoom here? Just like this. You can see it gets pretty damn vertical when it comes to its turning point. And if we look at the sine, this is kind of a turning point right here, right? If we were wondering, zoom out. So this arc up at the top above the x-axis to the x-axis, you can see it hits at like a 45-degree angle right here, which is very different to the way an ellipse or a circle hits over here. So we have a totally new type of arc. It's not a circle, it's not an ellipse, it's not a parabola, it's not a polynomial like you might have seen in previous classes. Let's ditch this sucker right here. So let's see, delete. So remember, you might have look at something like y equals, let's do a cubic. How about x raised to the third minus x. So this has a bit of a wave to it, right? In this middle here, kind of like, looks like a little bit like the sine function, but it heads up forever and then down forever on the other side. So a cubic is a special kind of curve. A quadratic parabola is a special kind of curve. And now we have this other new special kind of curve called a sinusoidal wave. So we're branching into a whole new kind of graph. Now that graph started on the unit circle, but we abstracted it off of the unit circle, right? So we took those y values off the circle and the angle, and we just looked at them as a table of values, right? Angle versus the y value. And if we plot those on a new set of axes, where the horizontal axis was the angle I started with and the vertical axis was the y value on the unit circle, then I get this crazy wave going on there. So I want to look at that in another graph, trying to wrap our minds around this. Let's let this one go away. And let's take a look at this one right here. We'll zoom in a little bit. All right, so what I've plotted here is this point A on the unit circle. And then the point B here, I did what's in my notebook. I took the point B has for an x value the angle that is formed right here between that radius and the x-axis, and its y value is the same as the y value of the point A. And what I just want to watch what happens is what the y value does as the angle increases. So I'm just going to grab this point A, I'm going to slide it down here, maybe, come on, point A, move. Why won't you move? You should move. Okay, maybe I have to use my slider to move it. Okay, there we go. And then let's see, my trace is on. So as I move that point A with my slider here, point B is going to have the same y value, but its x value is going to be the angle I make here. Right? So as A goes over to about here, then you can see I get up to the peak y value. That peak y value happens at pi over 2. Pi is around 3, 3 over 2 is around 1.5, and you can see the x value here is about 1.5, the y value is about 1. And then as we keep moving that angle around the circle, you can see then my y value drops, and then we get into negative values there. Let's slide this sucker over. Oh, the trace disappears when I move it. Let's put it back in. All right, so as I move A here, and my A, the little a is the angle, big A is the point, and B is basically the sine, the y value related to the angle. So there's that wave I have there. And we can move in a negative direction around. So if I adjust my slider here to go negative angles too, center that. As the angle goes negative, right, clockwise, I'm heading in the other way with the sine. And then I can go around clockwise, counterclockwise, and go the other way. Right, so we're turning the points on the circle into a wave by graphing the angle versus the y value. And we can do a similar thing with the x value. We'll try that next.